Dear friends, today we will discuss electric potential due to an electric dipole. So what is electric dipole? That you already know in the previous chapters. 2 point charges equal in magnitude, opposite in nature, separated by a finite distance, each called an electric dipole. I remind you about electric dipole. This is minus q, this is plus q, this is the electric dipole, and this line is called, the line joining the two charges is called axial line, and the line which passes through center of the dipole, this line is called equatorial line, and this dipole is called as ideal or short dipole when q tends to infinity and 2L tends to 0. 2L means the distance of separation between the 2 point charges. This is about the dipole. Okay, you have already read this dipole in the first chapter. Just I recall what you learnt in the first chapter. But today what we'll do, we will find electric potential due to dipole. First at any point on axial line, then at any point on equatorial line, then we will go to at any point, not on axial, not on equatorial. Just like we have done also intensity due to electric dipole in 3 cases, same thing also will do for electric potential. And another thing also, from the just previous class, we will bring one formula, potential due to point charge, this one, V is equal to KQ by R. Just I remind you, this is the formula we have discussed in the previous class, potential due to point charge. Another thing also I am telling you, very important, if Q is positive, you have to take its plus sign. If Q is negative, you have to take its minus sign. Suppose Q is minus 3 coulomb, while writing this formula, you will put there minus 3 coulomb, because potential is a scalar quantity. Okay, now let's come. We'll find, first we'll do any point on axial line. Any point on axial line. Okay, so this is the electric dipole, minus q plus q. I am taking, this is the direction of the dipole moment. I am taking the dipole moment direction along positive x-axis. This is the center of the dipole. This point is A, this point is B, and this distance is 12. If this the dipole length is 12, then this half is L and this half is L. C is any point on the axial line and a distance R from the center of the dipole. All these things, all these assumptions we have taken while calculating intensity in the first chapter. The same thing I am just repeating. So now what I will do to find potential at point C? These two are 2 point charges. I will find potential due to plus q charge. Then I will find potential due to minus q charge. Then I will add 2 potentials. Okay. Now let's write for plus q charge. What is potential? V plus. You can write V plus or you can write V1, but I wrote V plus due to plus q charge. KQ, this is the plus q charge. Here we will find potential. So which distance will take? B to C. So this is BC. Distance is BC. Then KQ, BC is how much? BC is SC minus BC. You take OC. BC is OC minus OB. Okay, KQ, OC is how much? R, OB is how much? L. Okay, is it clear? We have done in intensity also same thing, but we have done square there, because intensity KQ by R square. I am writing potential. Where is the direction of the potential? Where is the direction of potential due to this plus q charge? Is it along positive x-axis? It is along I cap, plus I cap? No, don't dare to think like this, because potential is a which quantity? Scalar quantity. It has no direction. Okay, don't write the direction here like intensity. Intensity is a vector, but potential is a scalar. Don't think about any direction in potential. Okay, so now potential into minus Q charge. V minus K minus Q. I had told you when charge is negative, you have to take negative. So minus Q, what is the distance? Charge is here. Potential you will find here. So it is SC. K minus Q. S is how much? AO plus OC. Okay, so it is coming K minus Q by AO. This is L plus OC. This is R. This is the potential into minus Q. Now we have two potentials. What is the net potential at this point? What I'll do? I'll add the two potentials vectorically? No, because they are not vector. I'll add them simply. Simple addition, it is easy to add two potentials because there is no vector addition, no triangular law, no parallelogram law. It is more easy than the intensity. Okay. So what is the net potential? V plus V minus. Now you put the expressions V plus this expression KQ by R minus L, then V minus, this is plus K minus Q, just this expression you put there by R plus L. Then KQ you take common, R minus L, R plus L, what is the LCM? A plus B whole into A minus B becomes A square minus B square. Then this is KQ, then it is R plus L minus R minus L. I take the LCM, okay, then this R plus L, then this R minus L, but here is one minus sign. So what is coming here? KQ. If I open the bracket, this R and R will cancel, minus will become plus. Okay, I am opening, I am doing one more step for you to understand easily. R square minus L square. Then it is coming KQ, R cancel, it is 2L by R square minus L square. Then what about Q into 12? You know, product of magnitude of either charge, distance of separation, this term. What is this? This is called dipole moment P, R square minus L square. So this is the potential expression due to an electric dipole. But if we consider for short dipole, means for ideal dipole, what happens? L very less than R. So L square can be neglected, it tends to 0. You remove the L square from here. L square, in place of L square you just put 0. So it becomes VKP by R square. This is the potential expression due to short electric dipole or ideal electric dipole. In exam, if question will come to find potential due to electric dipole at any point on axial line, you will do up to this much. You may or may not ask for short dipole, but you will do up to this much writing this condition for short dipole. Okay. So now let's come to equatorial line. Now I will do equatorial line. This is any point on axial line. Now I will do equatorial line. Any point on equatorial line. I have told you one name for that. What is the name? Broadside on position. Okay. And axial line is end on position. Let's come to this. So again we will draw the dipole. Minus Q plus Q, same dipole. Minus Q plus Q, A, B, center of the dipole. Center of the dipole here. Distance is 2L. So this is L. Also this is L. And this line is which line? Equatorial line. You can take upward, you can take downward, no problem. As your choice you will take. So this is point C. C is any point on the equatorial line at a distance or from the center of the dipole. Due to plus Q charge, V plus, same thing. We'll write for plus Q, we'll write for minus Q, then we'll add them vectorically. No, we'll add them algebraically, simple addition. Okay, so V plus K Q by Then this distance BC, KQ. What is BC? R square plus L square. Here is R, here is L. Use Pythagoras theorem, root over. Okay, then for minus Q charge, here this distance K minus Q, R square plus L square, root over. Same thing, this is SC. Okay, so R square plus L square root over, simply by Pythagoras theorem. We got the two potential. Then what is the net potential? V plus V minus. You add them. What we are getting? Very simple. Both terms are same. Only minus sign is here. So the net potential become 0. It will become origin. At any point on the equatorial line, if plus Q minus Q, two charges are there, you see, you take any point on the equatorial line. What about the potential? Potential is 0. Okay, so now we go to find potential at any point. At any point due to dipole. It is not any axial line, not any equatorial line. So this derivation in different books we will see. It has many ways books are doing, but I am doing one simplest way for you, so that will be easy to remember. Okay. Now let's see. One simplest way I am doing for you. Minus Q plus Q, two charges. Same thing. Point A, point B, point C. This is L. This is L. Okay. This is dipole. We consider. We'll take any point. Let's take the point here. Let's take the point here. This is O. Center of the dipole. We are taking O. This is endpoint C. Which is at a distance? Let's take the distance R, making how much angle? Theta. This is called polar coordinate. When you take any point, making an angle theta at a distance R, this R theta comprise polar coordinate. Okay, okay, you forget that now. So this the point is specified by R and theta. That's any point. That's not an axial line, not an equatorial line. So how will we find the potential at that point? We will find for plus Q, then we will find for minus Q, then we will add them. Okay, now see, for plus Q I am going to do. If I will do for plus Q, this is point B. For plus Q, see, this is the distance BC. Okay, so now for plus Q. For plus Q charge, what is the potential here? V plus, you write, or V1 you write V plus for plus Q charge. You see, what is the for plus Q charge? KQ, point charge formula, KQ by, this is BC, KQ by BC. Okay, it's KQ by BC. Now I will solve. I don't know BC. BC, can it be expressed in forms of R and L? Yes, we can do it. How to do? Let's draw one perpendicular from here. Okay, let's draw one perpendicular from here. If you draw one perpendicular from here, let's write this point as a D. So BC is the same as CD. BC and CD both are approximately equal to each other. So for which in place of BC, I write CD. You have to neglect this much here. Okay. So I can tell you that when you see two lines are like this. If from this longer line you want to cut the same length of this, then what you do? Draw a perpendicular. Then these two lines are same, almost same. I cannot say exactly same, but they are almost same. And how much difference is there? That will neglect in physics. Okay. So in place of BC, I wrote CD here. But what is CD? CD we can express, this is CO minus OD. CO minus OD. This much you do minus, then we get CD. K, Q, CO is how much? R. OD is how much? This angle is theta. This is one right angle triangle. This side is L. This L is the hypotenuse. Hypotenuse is L. This is theta. So this one will be L cos theta. Okay, this one will be L cos theta. This is the base. Okay, so it will be cos theta. to which side theta is in contact, that one will be cos. This is L cos theta. Okay, you can also check L cos theta. This is the potential due to plus Q charge. Now you go to find potential due to minus Q charge. Let's see for minus Q charge. This is the line become little bent. Okay, so this is the line. Okay, we find the potential due to minus Q charge. K minus Q. Again, I am telling you, when we take minus Q charge, we will write minus Q there. Okay, so minus Q. Then you extend it. You can ask one question here, but sir, while writing intensity, you have not put any minus in there. Why? Because intensity is a vector quantity. There we write direction. So we wrote only magnitude, then direction. There minus plus has no meaning because we are writing direction there. But in potential, it's not a vector, it's a scalar quantity. We have to put plus means plus, minus means minus. But while calculating force and intensity, we are writing direction. So plus minus sign will not take, we will write the direction there. Then K minus Q, then by SC. Then K minus Q. Again the same thing will do, we will extend it like this. Draw one perpendicular. Okay, draw one perpendicular. This is perpendicular. This point you take E. So AC is nearly equal to EC is equal to K minus Q. What is EC? That is OC plus OE. Then OC plus OE. Then it what happen? V minus is equal to K minus Q by C. OC is how much? OC is R. Then OE is how much? This again, if this is theta, then this is theta. Opposite angle. Then this is L cos theta. Okay. So R plus OE is L cos theta. L cos theta. Now we get the potential due to plus Q charge. We get the potential due to minus Q charge. What will do now? Vector addition? No. Again we will do scalar addition. So what is the potential now? V plus V minus K Q. Now take common. I am directly taking common here. 1 by R minus L cos theta. Then minus. Here is one minus sign. I took minus here. 1 by R plus L cos theta. Now take LCM. KQ. You take LCM now. A plus B whole into A minus B. R square minus L square cos square theta. Then this is R plus L cos theta minus R minus L cos theta. Okay, just I took LCM there. Mathematics I am doing. You all are expert in mathematics. It's not difficult for you. Then if you will open the bracket, R cancel, and this L cos theta will be minus, it will be plus. KQ 2L cos theta. Understand? L cos theta, then plus L cos theta, 2L cos theta by R square minus L square cos square theta. Q into 2L is what? Again the same question coming here. Dipole moment R square minus L square cos square theta. So this is the potential at any point due to electric dipole. But we will not leave here. Also we will go for ideal electric dipole or short dipole. If we do short dipole again, L variable less than R, L square tends to 0, that is neglected. So V is Kp cos theta by R square. This term is now 0. This is the expression of potential due to ideal due to short electric dipole at any point. Let's check what we have done. Is it correct or wrong? How will check? That any point can be a point on the axial line, that any point can be a point on equator line. Let's discuss now. This is now our expression. Let's come. Suppose this point now lies on axial line. Okay, first we'll do case 1. This C point now lies on the axial line. You see, the point is here. If the point will lie on axial line, now see how this line will bend. This line will bend like this. Okay, C point will come here. Gradually theta will decrease, and finally when the point comes to the axial line, theta becomes 0 degree. If theta is 0, V is how much? K. Here you put 0. Kp by r square. Understood? You see, when we did for axial line only, we get the same expression or not? Yes, expression is same. We get the same expression. Now come to equatorial line. If you do for equatorial line, what will happen? This C point will go to the equatorial line, means the line here. When the C point will go here, this is the equatorial line. Okay, what will happen to the value of theta? Theta will be 90 degree. What is the potential? Kp cos 90. What is the value of cos 90? 0. We have done potential on equatorial line. Directly we have done. Potential is coming 0. So that means our any point expression is 100% correct. But one important question must come here. So I will not leave here. I will tell you the important question what comes, just like after every derivation, after every theoretical practice, one question always comes there. Okay, what question may be attached here? If in exam this question will come. Okay, 1 or 2 more questions. It's a very important knowledge to remember. Potential is 0 here. You mark. I am now going to the question. So this is the dipole. Minus Q. This is the plus Q. This is the equatorial line. On equatorial line of the dipole, is intensity 0? No. What is the expression of intensity? K P by R cube. We have done intensity K P by R cube for short dipole. So here at any point on equatorial line, intensity not equal to 0. It has some finite expression value. Then, but what about potential? Any point on equatorial line, what about the potential? 0. This data make a question now. You can make a question here. Is there any point? Question is like this. You can note the question. Is there any point having potential 0 but intensity non-zero? So the live example is now in front of you. What will the answer? Yes. But if a student don't know this, then he may go in the wrong way. That if intensity, if potential 0, then how intensity will be 0? How intensity will be non-zero? But this is the live example. At any point on the equatorial line, potential is 0, intensity is non-zero. An exam question will come in light. Yes. Example, any point on the equatorial line. Also, this question may comes like this. Does 0 intensity point necessarily has 0 potential? Sorry, 0 potential point necessarily has 0 intensity? The question may come like this. Does a 0 potential point necessarily has 0 intensity? What's the answer? No. Potential is 0. That doesn't mean intensity will 0. Not at all. Intensity is non-zero here. Example is any point on equatorial line. This question may come in the reverse way. I am just changing the question. Okay, I am now making V non-zero, E 0. Question may come like this. I am making now V non-zero and E 0. What is this? How the question will come? Is there any point having 0 intensity but non-zero potential? 0 intensity but non-zero potential. Is there any point where intensity will be 0 but potential will be non-zero? Let's think. Yes. Yes, also this point is available. How you see? I'll take 1 plus q. I'll take 1 plus q. Just at the midpoint. Its intensity is here. Its intensity is here. Now both intensities cancel each other. If they cancel each other, what is the intensity here? Intensity is 0. But what about the potential? Potential is non-zero. How? Because there is here its potential is positive. Its potential is positive. They get added. Here potential is non-zero. So what is the example? At the midpoint of two equal like charges. At the midpoint of two equal like charges, E is equal to 0, intensity 0, but potential non-zero. You can also add another example here, which is also will be well known example. After some classes we will discuss that one. Inside a closed conductor. Inside a closed conductor, if this is made up of metal, inside it E is equal to 0, lines of forces cannot pass, but V not equal to 0. This is one example also. Inside a closed conductor, intensity 0 but potential non-zero. This question how will come in different language in exam, changing the little difficult language. Does a zero intensity point necessarily has zero potential? No. Live example is here. Intensity 0 but potential non-zero. I am repeating the question. Does zero intensity point necessarily has zero potential? Answer is no. Example, at the midpoint of two equal like charges inside a closed conductor. So this is all about potential due to electric dipole at any point on axial line, equatorial line and any point. Not axial, not equatorial. Also, two important 1 mark questions I discussed today. Thank you.